example is now taking advantage of the fact that we know how to deal with the dot product and we know a bit about position vectors as well, so we're going to look at finding the magnitude of an angle. Now as soon as I see the word angle, I immediately think, oh, this is going to have something to do with dot product, okay, because we know that the formula for the dot product has cosine of an angle in there, and this expression here, angle ABC, means we're trying to find the angle between these 2 points ABC. Now the first thing I notice is that we've got 3 points ABC, which are defined by position vectors, A, B and C. Position vectors, when they're written in this form, the IJK form, if it doesn't say, are given from the origin. So let's define the origin and let's put in these 3 vectors. I'm just going to put them in blue. I'm going to put them in a particular way too. Now this is very much arbitrary, but there is a reason for it. So I'm just going to label them. This vector here is going to be the vector A, and it ends in the point A. This vector here will be the vector B. It ends at the point B. And this vector here will be C, and that ends at the point C. Now the reason that I've done this way is because when we actually look at the question, we're asked to find the magnitude of the angle between A, B, C. That means, that we need to find an angle where B is in the center, because this implies that you've got the angle A to B to C. So B has to be in the middle. So that means that the angle we're trying to find is this angle here. This is our theta. Okay. Now you can see from the origin you've got your A, B and C. We're trying to find here 2 vectors, okay, and I'm going to call them position vectors in the way that they're going from 2 points. So this would be B to A, and this vector here would be B to C. And if we try and find those 2 vectors, I'll just do this over here. B to A, first of all, you can see that you'd have to travel backwards along this vector, which is the vector B, and then you'd travel forwards up this vector A. Remember that we have to travel from the tail of the vector to the head. So for B to A, it would be negative B plus A, and negative B is negative 2I minus J, plus A, which is I, plus 3J minus K. So putting all that together, we've got I, the J's we've got, and actually it will be negative I, because you've got negative 2I plus I. The J's, we've got negative J plus 3J, so that would be 2J left over, and there was no K's in the B, so we just have that negative K. So that's B to A. Okay, the next vector that we're looking at is the vector here, which is B to C. And you can see that if we want to go from B to C, again, we'd have to travel, I'll do this in another colour, do this in purple. We'd have to travel back along B, so from the tail to the head, and then along this vector, which is C. Okay, just rewrite that, doesn't look like a C. Oops. There's C. Okay, so we can do this now. So we've got negative B, we're travelling back along that B vector, and then we're travelling positively along C. So again, we've got negative B, which is negative 2I minus J, plus C, which is plus I, minus 2J minus 2K. I'm not having to change any signs here because we're adding. Again, with the I's, we've got, that's going to be negative I. Negative J minus 2J would be minus 3J. And again, we've got no K's except for this one, so minus 2K. Okay, so there are vectors, and I'll just write them here and put a little box around them as well, because they're going to be really central to the rest of the work that we do. So there's B to A and B to C. Now what we're interested in doing here is finding the angle, theta. So remember, if we want to find the angle, we can use the dot product. And in this case, our 2 angles are BA. So we do the dot product of BA and BC is equal to the magnitude of the first vector times the magnitude of the second vector, cosine of the angle between them. Okay, so we're now going to be working with, and I'll just move this to the left a little bit. We're now going to be working with the 2 vectors that we've found. Oops, just putting that over there. And then working and finding the dot product and the magnitudes. So I've just given myself a little bit of room here because I want to do that. So first thing here is the dot product. I'm going to do the dot product of BA and BC. Remember that for the dot product you multiply the coefficients of I, J and K together. So let's do that in some different colours. Coefficients of I, there's two negative ones, plus the coefficients of J, we add those on now, so there's a +2 and a -3, so we've got a 2 and a -3, plus we then add on the coefficients of K, so a -1 and a -2, so -1 and a -2. And we can see there, if we expand, we've got -1 times -1 is 1, -6 plus 2, so that would be -6 plus 3, -3. So we know our dot product here is -3. Next, let's find our magnitudes for BA and for BC. Square root of all the coefficients squared, so -1 squared plus 2 squared plus -1 squared, and that will be the square root of 4, 5, 6, square root of 6. And a magnitude of BC is again the same thing, square root of the coefficient of I squared, the coefficient of J squared, and the coefficient of K squared. 9 plus 4 is 13, plus 1 is 14, so this would be root 14. Okay, so we've got our magnitudes and we've got our dot product, so we can put those in, root 6 and root 14. Cosine theta. Okay, and to finish off, what we're trying to find is the angle to 1 decimal place, and the 1 decimal place implies that we can use our CAS. So by doing that, we're going to then use our CAS to solve for theta. So all I'm going to do here is just re-express this, and I might just do that here. So cos theta equals, we've got -3 divided by the two magnitudes, root 6 and root 14. Okay, and again, to find theta, there'd be one final step, and I'm just going to erase this section here. I'll just get rid of that section, that's enough. So we finally have theta equals inverse cosine of, and I'm just taking the cos over to this side, -3 over the square root of 6, square root of 14. So to do that, we're going to use our CAS. In the CAS, I'm just going to put that in, so inverse cosine of -3 on root 6, root 14. Incidentally here, just to save yourself a bit of effort in the CAS, you can actually combine these two things together because they're both square roots, so you can put them on the same one. So we've got inverse cosine, so inverse cosine, -3 over square root of 6 times 14. Now my calculator is currently set to radians. Remember to check it just to make sure. So settings, document settings, yeah, I'm in radians. So the value here that I'm getting is an exact form in radians. We're allowed to find that correct to 1 decimal place. I'm just going to press Control and Enter. I've got 1.90. So that means that the result here would be approximately 1.9, and it only wants to 1 decimal place. So 1.9 radians. Okay, so I'm using that little form there for radians. And again, if you wanted to put that into degrees, you could do that as well. So it'd just be the same thing. So going back into your CAS, and just going into your home, changing your settings to degrees, and then just finding this again. Oops. And again, I've got mine set to exact, so 109.1. So 109.1 degrees if you want it to be that way. The question doesn't actually state that it wants it in radians or degrees. The more common way of giving angles in vectors is usually to use degrees. So I probably would be using this 109.1 degrees for this question. So the key thing here, finding magnitudes of angles, really read the question, understand that the position vectors help you to find the other position vectors between the points, okay? Find the magnitudes of those position vectors, and then using your dot product formula, which is down here. So again, the really important formula, using that formula, rearranging so that theta is the subject, and you can then find your angle in between those two points.